In section 4.2, we're going to continue to talk about some other important applications of differentiation. Now, if you take a look here at the opening motivation, you'll see that I'm asking the question of what is an example of a function that would be easy to calculate for some inputs, but may be quite difficult to compute specifically by hand for other inputs. Okay, so you can start thinking about all the different sorts of functions that you know. And some maybe standard functions come to mind, right? Maybe some possible examples of some functions here could be things like a trig function, right? Maybe the sine function is really easy to evaluate by hand for some values, right? Like the sine of 0, sine of pi over 2. But for other values, this could be extremely difficult. Like, what's the sine of 1.6? You're like, I don't know. And how would you compute that without the use of a computing device, like a calculator or going online? Well, this isn't necessarily the only function, right? I mean, we could think about what about y equals e to the x? Really easy if I pick x to be 0, but pretty much anything else is difficult, at least to get very accurately. I could even do some other complicated functions like the natural log function, right? I could even do something as seemingly simple as a square root function, right? Because in a square root function, it's really easy if I'm plugging in perfect squares, but what if I plug in something like pi into there? Then that's actually going to be extremely difficult to calculate, again, by hand. And so one of the goals in this section that we're going to have is to see how we might be able to actually evaluate functions like these at somewhat difficult numbers. And we're going to use our understanding of derivatives and tangent lines to help us do so. So let's go ahead and kind of lay the groundwork for what we're going to try by maybe focusing on something like this square root function. So I'll say here, let's suppose, for example, that we want to approximate the value of the square root of, say, 3/2. Now, I, of course, am going to want to do this without any computing device. So that is, I'm interested in how would I do this if I didn't have a calculator, if I didn't actually end up with, like a website that could compute this for me. And if you think about this, this is actually a really meaningful question, because even though I know my calculator could do this, or I could type this into Google and I could immediately get an answer, how do those items, how does that, how does Google, how does my calculator actually know how to compute this value and give me an accurate answer? Where does that come from? Who programmed these particular things to spit out certain answers, and what did they program them to actually do? Well, this is kind of the goal of this section. We want to try to figure out how we do this again without any computing device. And so I'm going to ask right now that you don't have any calculators out, don't have Desmos open, nothing like that for the moment, because I don't want you to see what any of these values are directly. I want you to kind of sit with a big cloud for the moment over what this value might actually be. But we're going to come up with a way to try to compute this. So let's see how I'm going to propose that we do that. So I'll say, to do this, notice that it would be easy to find a tangent line to the curve f of x equals the square root of x at x equals 1. And the reason that that would be easy is because I know that the square root of 1 is actually really easy to compute. So let's take a look at how we would do this. I kind of have a set of axes already set up on my page. You could draw one out on yours. But take a look at what would happen here if I just draw out what the square root function roughly looks like, right? I know it starts at 0, 0, and it comes out like this. So I know that if I tried to plug in the value of 1, I would very, very simply and easily get back the value of 1 up here. So that point is super, super simple. And I know that I can go ahead and I can sketch a tangent line out on my curve here, and I should be able to find the equation of that tangent line no problem, right? Super, super easy. Now, what I see is that I'm trying to actually approximate, though, the value of the square root of 3/2, or 1/2. Well, notice what that would mean is that if the value of 1 is here, let's say the value of 2 is right there, then my value of 3/2, or 1/2, is right here. And so what I'm really looking for is this y value, right? That's what I'm trying to find. But I recognize that that's actually really difficult. So I'm going to build this tangent line and then try to use it to show something. So first let's try to find the equation of this tangent line. Remember that I'm going to need a point and I'm going to need a slope. So I'll start with this. Note that if x is equal to 1, notice that's again where I'm building my tangent line, then f of 1 is equal to 1, and f prime of 1 is going to be equal to 1 over 2 square root of x, and so it's going to get me a value of 1/2. So what I'm going to end up with is a point of 1, 1, and a slope of 1/2. And so the equation of my line would be as follows. Write this out here. Equation of the tangent line would just be given by y minus 1 is going to be equal to 1/2 times x minus 1. Now, if I write that in slope-intercept form, I'm going to get a 1/2 x. Notice here I'm going to get a negative 1/2 when I distribute my 1/2 here. And then when I add 1 over, that's going to give me positive 1/2. So here's the equation of my blue tangent line. And now that I know that that equation for my blue tangent line has this form, I should notice something here about the pictures. Again, we should be able to agree that plugging 3/2 into my black function, f of x is the square root, is really difficult to do. But what if instead I plugged 3/2 into my function of the line? That is, what if I plugged 3/2 in here? Notice I would get this red y value, right? It wouldn't be the y value that I'm looking for, but it would be pretty close, right? And this is kind of our idea. I should be able to notice the following. I'll say, notice that the tangent line is really close to the actual curve. The tangent line itself is actually really similar to the square root function, but only for x values that are near 1. Right? I mean, because I can see here that if I stay pretty close to the value of 1, I can see there's almost hardly any difference between the function itself and its tangent line on this little interval. But the further away I go from 1, I can start to see that the gap between the blue function and the black one continues to grow. So my tangent line is really close to the actual curve as long as I have x values that are near the value of 1. So another way to state this would be that f of x is pretty similar to y of x for x values near 1. Now this is really interesting, because what this means is that I could say that to approximate the square root of 3/2, we could then just evaluate the tangent line at x equals 3/2. So notice what I can say. Square root of 3/2 again is what I would get if I went to my original f of x function right here and I plugged in 3/2. That's this dot right here. That's the one I'm looking for. And I know that the answer for that is roughly the same as going to my tangent line and plugging in 3/2. But the advantage in doing this is that plugging 3/2 into my tangent line is something that I could compute even without the use of a calculator. Like, take a look. Let's see here. This is going to be, what, 3/4 plus 1/2, or 0.75 plus 0.5, or I could write that as 1.25. So overall, I can state that the value of square root of 3 over 2 is roughly the same as 1.25. They're roughly equivalent. So this is kind of the general idea of this section. Can I use a tangent line to estimate the value of a difficult value that to compute? Now, what's kind of cool here is that you could actually see that if you were to go use a calculator here, and I'm going to go ahead and pull up a calculator that I have, if I was to actually type in the square root of 3/2, I can see how close my answer of 1.25 is to the right answer. So the right answer is apparently 1.22-ish, and we were guessing 1.25. So without knowing pretty much anything at all about this value to begin with, and just using some simple calculus, we were able to get the ones place correct and the first decimal place correct. We were actually even really close on the second decimal place. So that's pretty interesting. Now, one of the questions that we're going to ultimately have, as I state down here, is how can we tell how far off our approximation is going to be? You know, like if I get 1.25 and I don't know what the right answer is, how do I know if this is any good? How do I know if it's close or not close? Especially if I don't, again, check a calculator to see what the real answer is. Well, one unfortunate thing here is that I can't really answer that question at the moment. It's a very important question in areas like computer science, but this is something that we'll actually be addressing more in Calculus 2. So in Calculus 1, we're kind of stuck, as I state here, in just providing an approximation, but not really knowing how good it is unless we use the calculator to check it. Now, one final thing before we go ahead and kind of end this video is going to be the following definition. What we're going to see is that the construction of this tangent line becomes very useful for finding or estimating this difficult y value that we have up here. And so instead what we're going to do is we're going to see that we're going to give our y value right now, or sorry, our tangent line y value, a very special name. Instead of creating a tangent line that's going to be called y equals, we're just going to go ahead and change that to look like L of x equals. Now, don't worry about the rest of this formula. That's not necessarily super important. We should just notice that this thing right here is just a tangent line. And so we're going to say that we can call a tangent line in this section a linearization of our function at a point. A tangent line is a linearization. And when we make the comparison that says our black function f of x is roughly looking the same as our tangent line, we call that a linear approximation of the function at a particular point. So in the above motivation, we found a linearization of our function of the square root. It was at the x value of 1, and we had our linearization was 1/2 x plus 1/2. Notice it's the exact same formula here. I've just replaced this value of y with an L. So a lot of times people get a little bit freaked out sometimes when they see these new words, but just remember, if you ever see linearization, if you're asked to find a linearization, you know that you're just really being asked to find the equation of a tangent line.